Welcome back. So hope if we can start back again to complete that part. At the end, we will have those YouTube links. So if you want to go through it one more time. So we just need to continue with this part. So as I told you, if you want to get access to those intermediate values, you need to define a different model, TIL model, and the input to those model will be the input to my original model, and the output will be the output from any layer if you want to get access to any layer of your model. So in my case here, I need to print out the outputs from RNN layer. So the outputs will be model.layers0. It's layer number 0.output. And this is the model summary. So the model summary, it's okay, the same, no changes, the same number of parameters. But the shape of the output will change, as you can see here. So the shape of the output will be different, right? So it will be 3 times 10, correct? It will be 3 times 10. 3, it's number of steps, and 10, it's the size of the hidden states. So in this case, we will get 3 times 10 outputs. And as you can see here, when we are printing those outputs, we got 3 times 10. So the first vector, it's the first hidden states. Maybe it's just maybe the first output was H1, for example. It could be, for example, H1, H2, and H3, for example, one from each activation. So number of parameters will not change, but the size of the shape of the output will change. So last time it was 10 because we tried to get access only to the last hidden states, which is H3, for example, each time. So it was 1. We can go back to it. So the output shape was 10, as you can see here. So the output shape was 10, right? But when we use this return sequence equal true, in this case, the output shape will be different. It will be 3 times 10 because we will get access to those 10 hidden states in each repetition or in each activation, for example. So the output shape will be 3 times 10. And when we are printing out, you can see that those are the 10 values, right? There is something called a time distributed layer, and it's how to apply a dense layer on multiple outputs from the RNN layer through rubber layer called time distributed, and it will apply the dense layer on each output, and it gives us plus probability scores for entities. So it says the model will be the same. I mean, our model it's the same, but remember to use return sequence equal true, so we can get those hidden states or any outputs. And after that, we will use this time distributed rubber layer, for example. And we need to define it. Inside it, we need to define our softmax layer. So softmax layer will be the same. So we will try to get 3 outputs from by applying those 3 outputs to each hidden states or each output, for example. So in this case, we will get in each activation, we will get some output probability. Maybe it's the next character, whatever. So it will be like this one. There is also something called the stacking layers and how to stack multiple recurrent layers one after another. If you want to make it more deep, we need to use those stacking layers. So note that we need to set return sequence equal true in the first layer while we set it false in the last layer. So you will have stack of RNN layers. The most important is that in the bottom layers, we need to use return sequence equal true, but for the pop one, the last layer, we need to set this one equal false because we need to feed only the output to the softmax layer, right? This one. So for the bottom layers, we need to set return sequence equal true because I need to get access to those. We need to feed those to the next layer as an input, but we need to set it equal false for the last layer, so we can just focus only on the last output if it's sentiment analysis. So it's a sequence to sequence stacking RNN layers. We need to have this RNN layers more deep. So in this model here, as you can see, so I will use the first RNN, simple RNN with 10 outputs. The input shape, it will be 3 times 3 because each sentence consists of 3 characters, and each character is represented by one hot encoding of size 3. Return the sequence equal true. I will use another simple RNN. In this case, number of outputs units, number of hidden states will be, for example, 5. Return the sequence equal true. In this case, or Of course, it will be true if you want to have sequence to sequence, and it will be false if you want to use sequence to one. And at the end, we will have this dense layer. I don't know if you need to use this one in time wrapper or not. I don't know the difference, in fact, if you will use it as it is like this one or in time wrapper. You need to combine the model. This is my data set. It's sequence to sequence. So when input is ABC, the output will be BCA, and so on. You will train the model. This is number of parameters. This is the first layer. It's 140 because we didn't change anything for the first layer. The last layer, it's 18 because number of units in the second RNN, it's 5. So number of parameters here, it will be 5 times 3 plus 3, right? So it's 18 because it's inputs to this dense layer, it's 5. So it will be 5 times 3 plus 3 equal 18. For the second RNN, we have number of units equal 5. So recurrent weights, it will be 5 times 5. And the input weights, it will be the outputs from the first RNN layer, which is 10 multiplied by 5. So it will be 10 multiplied by 5 plus 5 bias. So it will be 80. You can define temp model also, and you can get access. Those numbers are it's 9 outputs. I don't know what are those 9 outputs. Yes, it's the output from the soft. It's the outputs from the soft layer each activation, correct? So for example, when the input is ABC, the output should be BCA, correct? Yes. For the training, for the test set, I mean, we have here test set. So as you can see here, this is X test. For example, when the input is ABC, we should expect when input is ABC, we should expect the output to be BCA, right? When we do this, we got this output from the dense layer, right? So in the first activation, the output will be 0. As you can see, 0, 1, 1. This one will just replace it by 0, 1, 0, correct? The second, it will be 0, 0, 1. 0, 1, 0, 0, 1, 0 is 0, 1, 0, it's B, correct? So 0, 1, 0, it's B, right? And 0, 0, 1, it's C. And 1, 0, 0, it's A. So when the input sequence is ABC, we will get BCA. I mean, because we calculate probability, I mean, the output from the soft max layer, it's probability, so we will get those numbers. Those numbers are probabilities, and the summation of those 3 outputs should add to 1. If you want to convert it into 0, 1, 0, for example, you need to use this argmax, nb.argmax or whatever. So you can convert this first vector into argmax. It will be 1. You will get 1. Apply argmax to the second output, it will be 0, 0, 1. So you will get, it will be the index of the largest value, which will be 2. And this one will be 0. So it will be 1, 2, 0. And 1, 2, 0, in fact, it's a BCA. We need to use, those models are just meant for time series and text, but if you want to use it for image, because we can use, but also for image, because we can use image captioning, for example. So the input could be an image and the output could be a description, or it could be a class. So I need to classify MNIST dataset using RNN. Model based on RNN can process each MNIST image as a sequence of. RNN cannot consume this image as it is similar to CNN, but we need to convert it into sequences of. So I need to divide it, split it into those sequences. So it could be 1 pixel times 28, because this image is 28 times 28. So I need to slice it into this format, right? So it could be like this one. So it will be 28 times 28, correct? So I need to flatten it. In fact, it's just to flatten it. You can use flatten layer, for example, to do this. So I will do this one. So I will convert this image from 28 times 28 into 1D vector, correct? Which will be size 28 times, it will be like 1 times 28 times 28, correct? So this dimension, it will be 28 times 28. So each, or you can say that I will convert this one into input shape of, in fact, it's a 28 times 28. 28, correct? But in this case, it will be number of repetitions will be 28, number of repetitions, and this is the dimension of the input. So this is the input dimension, correct? So in the first activation, I will send one vector. I will send this one in the first activation, and in the second activation, I will send the second. I will send the second slice or sequence, and so on until we do it. So I will build RNN, but just remember that this RNN, it will do 28 time steps or 28 repetitions or 28 activations, and in each time we will send this a vector of 28 values, 28 pixel values, right? So the model here, it will be, we need to load the data set. So I mean, this is MNIST data set, as we know, right? And we need to normalize the input data. So I will just divide each pixel value by 255 for the X-train X-test. I will use one-hot encoding because Y-train, we have 10 classes. So the input shape, it's like 0, 7, 8, 5, 6, 4, 3, 2, like this one. So I need to use one-hot encoding to make it simple for my model. So I will convert this one into one-hot encoding using this two categorical function. I need to build my model. So it will be this number of units. It's a hyperparameters. You need to decide it by yourself. Someone will select 128. So 128, it will be number of hidden states, right? So it's something which you need to decide. So the input chip, as I told you, it will be 28 times 28. So because each time we will feed one slice, and each slice will be 28 pixel values, and this is the number of repetitions. So we do this 28 repetitions. I will use activation function ReLU because it's a number between 0 and 1. So it's okay to use ReLU, for example. We will use dropout because I feel that number of parameters here will be too high, and it's smart to use dropout to avoid any overfitting. And the output dense layer, it will be softmax layer of 10 units because I need to classify into image into one of those 10 classes. We will use loss function categorical cross entropy. Anyway, just this is model summary. Plot your model, those number of parameters. So output shape, it will be 128. We know, we understand it, right? Because we said that we will use number of units equal 128, and the number of outputs will be equally will be the same. Number of hidden states or number of outputs will be 128. So the output shape will be 128. For the dropout, it does not have any parameters. We know this because the dropout, it's a technique which we use to avoid overfitting. And the output shape for the dense layer, it will be 10 because we need to classify each image into one of those 10 classes. Now we need to calculate number of parameters here. How can we calculate this number? Can you help me, please? So first, we have two types of weights. We have this recurrent weights. So the size of recurrent weights, it will be 128 multiplied by 128. So this is the recurrent weights. We call it recurrent weights. What about the input weights? Input weights, it will be 128 multiplied by the dimension of the input shape. Input shape, it's 28 pixel values. So it will be 128 multiplied by 28 pixel values. And we will call this number is the input weights. What else we have? We have number of bias. The number of bias equal to the number of units, which is 128. Multiplying, summing, so it will be 20,096 values. For the dense layer, if you need to calculate this number, I have 10 outputs. What about the inputs? The inputs will be 128. So it will be 128 multiplied by 10. 128 states, hidden states, the size of the hidden states, the dimension of the hidden states, it will be 128 multiplied by 10 plus 10, we will get this number. We trained the model because we have X training and X test. We trained the model, as you can see, I trained the model for 50 epoch, and we can get the classification report. And we have 10 classes. So some classes, I mean, most of those classes are very well. The overall accuracy, it's 96%, right? Overall accuracy, it's 96%. And this is the precision, recall, and if score for each class. And I advise people to do this because usually, even if you are working with multi-class classification problem similar to this problem, usually people just refer to the overall accuracy and overall also this is macro. I mean, this is the precision and recall. Also, this is the overall. So those numbers, maybe it's okay to report those numbers, but also it will be very smart if you can report precision, recall, and F score for each class, right? Number of support, it's number of samples in each class. So in class 0, for example, it was 980. So as you can see, it's not balanced, right? Some classes are more represented than others. So, but it's fine. So this is the confusion matrix. So if you want to get the confusion matrix, I mean, so we can see that it's a fine. So it's 967 from class 0 was classified as 0. This one from class 1 classified as class 1, class 2 until class 9. So you can see this is a confusion matrix, and this is the overall accuracy, precision, and recall, and F1 score. You can go to this example and you can play with this example. But if you have any questions, please. Any questions, please, for this example? This example is nice because here we are just MNIST. We use the MNIST before with MLP. We use the MNIST for CNN. Now we can use RNN or simple RNN for classifying MNIST datasets. We want also to use find an example for time series forecasting. And the time series forecasting, it refers to the process of predicting the future values of a time independent variable based on its historical values, right? So the time series is simply a series of data points ordered in time. Time series is a sequence taken at a successive equally spaced points in time. So if you are working with temperature, for example, we cannot shuffle temperature because it will make a problem. So if I record, if I have, for example, temperature recorded over a year, we have seasons. So we need to keep the order. If you try to shuffle it, you will destroy your time series. We have very nice data set called the airline passenger data set, and its time series data set that contains the monthly totals of international airline passengers from January 1949 to December 1960 in units of 1,000. And the data set contains 145 observations for 12 years. So each year we have 144 observation, where each observation corresponding to a monthly count. So in this data set, in fact, it's 12 years data set, where we have we have monthly, I mean, number of airline passengers, right? So if you want to predict how many will travel next month, for example, you can use this data set for predicting it. So the data set exhibits this clear seasonal pattern with higher passenger counts. I mean, of course, people travel more in summertime and the lower counts in the winter time, right? So this is the seasonal impact. And the data set is often used as a benchmark data set for time series forecasting, where it is used to test the accuracy and the performance of different. I mean, when it's a benchmark data set, usually people use it for testing algorithms, right? Because it's easy, I can download it. Okay. Okay, I guess. I have something. Siri, stop, please. Okay. Yes. Sorry, I will just share my screen one more time because I had some problem here in my computer. So I will, but if you have any questions, please, you can just ask those questions until I share again my screen. Yes. So it's a benchmark data set which is used for testing algorithms. Can you see my screen? So this is the data set. Yes. So we have here 144 months. So this is time. It's from 19 something. So it's months here. Maybe we can write here. Sorry. Maybe it's smart to just write here that it's months. Right. So time here in months, for example. We have 144. And this is the data set. And you can see that it's increasing over time. We have this seasonal impact. This is the summertime, right? And this is the winter time, because people prefer to travel a lot in summertime, for example. This is the number of passengers in 1,000, right? So you can see that at some point, I mean, there are maybe Okay, but it's normalized. I mean, this data set is normalized. So, for example, in January 1949, it's 112,000, right? But here in this y-axis, it's normalized. So to use this data set, it must be converted into inputs, input features and outputs, which is target feature, because it's 1D, in fact. This data set, it's 1D. If I need to use it for training RNN, I need to convert it to inputs and outputs. I need to get input features and target features to train my model to predict those numbers. So this is the data set, how it looks like. It's a sample or months. I can just call it samples or months 0 months until 143, for example, each month. And this is the number in each number of passenger in each month, for example. There is something called the look back, for example, which means I can just use one value for predicting a future value, right? So I can use the value in January 1st to predict the value of next month in February, right? So this one, it's January for February. And in February, 118 to predict the in March, 132, and so on. So in this case, the time window equal 1, which means I will use the most recent value for predicting a future value. If you need to put it in the correct shape, so it should be in this format: number of samples multiplied by the time steps multiplied by the features. When we do it, how many time samples? So it will be 140. I mean, we have 144, correct? 144. Sorry, this one maybe it's wrong. This one should be 143, right? Because we are starting from 0. So this one, it will be 143 multiplied by 1 multiplied by 1. So 1, it's the input dimension, because the input dimension, it's just a single value and it's integer value. In fact, it's not even float value. So the dimension of the input will be 1. Number of repetitions or the size of the window will be 1, which means I will use the most recent value for predicting next month's value. You can do it in another form also. Okay, in this case, I will just build my model. I loaded my data set here, and I will normalize my data set. I just normalized it to be sure that each feature, I mean, the feature range will be a number between 0 and 1. As you can see when we are plotting it here, it's normalized. And I need to split the data into one part for training and one part for testing. So I will use 70% for training and the rest will be for testing. So that part will be 70% will be used for training and 30% will be used for testing. And as you can see here, we didn't shuffle the data set, because if you will shuffle, you will destroy the time series. So the test set, it will be the first 70% values, and the rest will be used for testing. Now we are plotting my data set. So the green one will be used for training, and the red part will be used for testing, right? So now we have a time step. As you can see here, we have a time step because we just used the one time step. So I will use, here I will use only time step equal 1 because I will use the most recent value for predicting a future value. If you want to use 2 time steps, in this case, I will use the value from January, February for predicting March. January, February for predicting March. February, March for predicting April, correct? And so on. So in this case, the time step equal 2. So the shape will be like this one. It will be 141, which is the number of samples, and comma, time steps equal 2. So the size of the time window, it will be 2, but also still the input shape is 1 for the input because I have its integer value, right? So I build my model for one time steps. I used RNN here. I mean, you have this code for doing this. I mean, this is the code which will put the time series in the correct format because I need to generate X training and Y training. So we will do this using this time. I mean, the time series. The input to this one will be the time set, which is the time series, and the output will be X and Y. I mean, the output from this function it will be X and Y, right? And you need to define here the look back, which is 1. When it's 1, it means it's 1 time steps. When it's 2, it's 2 time steps. When it's 3, it's 3 time steps. So you need to define the model. So I will use symbol RNN. It has 4 units. The input shape will be this time steps, comma 1, right? And I will use dense layer for with linear activation function because we need to predict the future values. So it's not softmax because we are not calculating the probability, but we try to predict future values. So I used here the units equal 1 because it's a single value which we need to predict, and the activation will be a linear function because I need to regress, right? We are not classifying, but we do some regression. So in this case, we will use linear activation function here. As you can see here, because it's a regression problem, so the loss function will be mean squared error, right? It will be mean squared error between actual desired value and actual value, or true value and predicted value. This is the input is 1, output is 1. For the simple RNN, the input is 1 and the output is 4. Why the output is 4? Because we selected a number of units here equal 4. So the input is a single value and the output will be 4 values. Those 4 values, in fact, it's the dimension of the hidden states, right? So each hidden state will be represented by 4 values. So it will be, so the input to the second layer, the dense layer, it will be 4. The output will be 1. Now, if we need to calculate number of parameters, it's very, very easy. So for the first layer here, for the RNN, it will be 4 times 4, 4 times 4, plus 4 times input, which is 1, plus 4. Right? So it will be 24. Number of weights for the output layer, dense layer, it's easy. It will be 4 plus times 1 plus 1, so it will be 5. So total number of parameters will be 29. Now we will train the model. I trained the model using X-train, Y-train, and I will test the model using X-test. And I'm just plotting here. I mean, the green part, it's maybe it's X predicted for the. I mean, as you can see here, for the training part, it's perfect, which is expected. But for the test part, you can see that there are some difference between actual value and the predicted value, and this is okay because we should expect that the error in the test set will be much higher. So you can look into this blue and red. The blue, it's the true value, and the red, it's the predicted value, and we follow the same. I mean, we have the same seasonal effect at least, right? We have some errors. Of course, you can. I trained this model for 100 epoch. Maybe if you will train the model for longer time, you will get much better accuracy, right? If you will use 3 time steps, in this case, we will use the most recent 3 values for predicting a future value. We should expect that we should get more accurate predictions, right? And as you can see, the model parameters will be the same. It's a surprise, right? Number of parameters will be the same, although we have 3 time steps. I mean, when it's 1 time steps, we will have only 1 activation each time. For each prediction, we will have only 1 activations. But in case of 3 time steps, so for each predicted value, we will do 3 activations. So it will take more time, but it will not impact the model complexity. The model parameters will still the same. It will be 29. So there is no change, but we should expect that. So the time window is larger now. So I'm using the most recent 3 values for predicting a future value, right? If you need to compare between RNN and LSTM and the GRU, for example, this is RNN, this is simple RNN, which is very simple, right? This is our RNN. We have been working now with this RNN, very simple one. So we just calculate the states as a function of xt, ht minus 1. We use this hyperbolic tangent, and we calculate ht, and from ht we can just get output. The output, it could be ht, or you can just apply softmax layer on h of t to get output of OT, for example. So this is very, very simple one, very, very simple one. And the input dimension, it should be, my data set, it should be like a number of batches or samples multiplied by time steps, multiplied by features. We did that before already. For GRU, it's more complex. As you can see here, it consists of number of gates. It's a gated recurrent neural network, recurrent unit, for example, GRU, and it consists of number of gates. If you want to go into more details, please go to it. So if you need to calculate HT, for example, first we need to calculate R of t, which will be a function of x of t, ht minus 1. We calculate this one, and after that we will calculate ZT, and after that we'll get h of t. So it's more calculations, so it's more complex, and of course more parameters. But I mean, for in long-term, short-term, long short-term memory (LST), it's more complex also compared to GRU. But for us, I mean, in terms of programming, it will be the same. It consists of number of gates, and those gates, they have some functions. You need to get f of t, I of t, c of t, o of t. So it has some number of equations. I will not go into much details here, but I can go also for just explain GRU, for example. So GRU adjusts the information flow by using two gates. It has two gates, update gates and the reset gate, that determine information supply to the output. So it try to control how much information should be, transferred from between, adjust the information flow by using two gates, update gates and reset gates. The reset gate regulates how the signal input xt is combined with the hidden states ht-1. This one reset gate, R of t, it's a reset gate. And the update gate, which is Z of t, determines how much of the previous memory ht-1 is preserved, right? So, and after that, we will calculate ht as normal using hyperbolic tangent. So Z of t, it will be this sigmoid, which will, the activation function. This one, it's sigmoid function, right? So it will be sigmoid of x of t multiplied by omega plus ht-1 multiplied by u or something. We will go to so we will calculate Z of t, and after calculating Z of t, we will calculate R of t using sigmoid also. So it will be x of t multiplied by omega plus ht-1 multiplied by u. After that, we will calculate the hidden states using hyperbolic tangent, as we did before, right? And after that, we will calculate ht dash. From ht dash, we will calculate ht, which will be 1 minus zt multiplied by ht-1. So now we are calculating. Do you see this one? How much? Because this is the update gates and the reset gates. So reset gate, it will determine how much information supplied combined with ht-1, and the update gate, it will determine how much of the previous memory ht is preserved. This one. So if ZT is too high, we will preserve less. If ZT is small, we will keep more from the previous hidden states. So just the equations, you can just go to those equations if you want. So now I want to use IMBD sentiment analysis one more time using one of those models, for example. So it's text, it's a sentiment analysis where the input is a text and the output will be a binary classification problem plus and minus, for example. So this data set, we need to, we just import it. We need to define maximum words. So set the maximum number of words to include the vocabulary. This is my dictionary. So if you decided that your dictionary size will be 20,000, which means I need to pick the index of the words which are most popular. How many most popular? It's 20,000 most popular words. So this one will be my dictionary. So this is my data set. We imported it. So we will import, it means we load IMDB data set with the most frequently occurring 20,000 words. We will ignore the list. It's a kind of truncation, in fact. So this is initial X train 0, for example. So this is how it look like, as you can see. So this is the first review. And this first review, it's a bunch of, it's 1D vector of indices. Those indices are the indices of the most frequent words in my dictionary, in this maximum words of 20,000. So the first one, for example, it's 114. It's a one word, which is most common. 14. So it was a sequence of words. So we will pick the most frequent words, and we will give it an index. So this index, it will be a number between 1 and 20,000. So this is so the first review, for example, it consists of 218 words. As I told you, some reviews are long, some reviews are short. So the first review here, it's 218 words, and this is the index of each word in this review. And the second review, it consists of 189 words, and this is how it looked like. So because as I told you, if you need to use MLB, right, we need to use truncation. I cannot use the first input, it cannot be 218, and the second review, it should be 189. It will be impossible, right? We cannot do this. If we need to use MLB for doing this, we cannot use a variable length of input vector. It will be a problem. It's impossible. So in this case, we need to decide, for example, the length of the reviews, right? So you will have those reviews. Maybe you can just decide by yourself. I can just use 100 words, for example. If I will use 100 words, so this is shaded part, it's 100. So I will use the first 100 and I will truncate the rest. I will ignore the rest. So in this case, I will use only the first 100 words for to feed it to my MLP, and I will ignore the rest. So for example, set the maximum length of the input sequence is 100. If we use it 100, for example, so in this case, X train 0, it will be converted into this one, from 1 to 16. And from 1 to 16, it's the first 100 words, right? If we can go back here, from 1 to 16. So this is the first 100 words. The rest, what about the rest? Ignore it. So in fact, it's information which we ignored. If you want to use MLP, in this case, we will lose all that part. We will ignore it. It's a truncation because I need to select an input vector of fixed size. So in this case, if I selected 100, I will ignore the rest. If you selected it to 100, I will ignore 18 here at the end. But for the second review, it will not be enough. So I need to use zero padding. So I need to fill in the rest by zeros, correct? So this is if I will use 100. So X train 0, it will be like this one, and X test 1, it will be when it's 100, it will be X test. Oh, sorry, this is X train 0, X train 1. It's okay because we have too much input. But for the test set, I try to get you an example which has less number of words. So X train 0, it will be okay. We will use that part. But remember that for X train 0, we truncated the rest. We ignored the rest. For X test 1, it was not enough. In fact, it was less than the maximum length. So I need to use padding, zero padding, to fill in the rest. Zero padding, right? Which might cause a problem to my model in the training process. So this is the problem. In fact, this is the problem when we are working with MLP. We need to deal with this problem when we are working with MLP. So if you will use this zero padding, it will impact the training process. If you will use this truncation process, it will be a problem. But if you want to work with a recurrent neural network, you don't need to worry about this problem at all. I don't care if some people give short review and some other people give a longer review, because the impact will be number of repetitions, number of activations, not model complexity. So I will use here LSTM. I defined we need to use this embedding layer because I need to represent each word as a vector of a length of 128. So this is word embedding. It's very, very important because I cannot work in machine learning. I cannot work with text numbers, text values, for example. I need to convert those text into a vector of numbers. So I need to use word embedding. Maximum number of words, it's something which you need to decide. And the input length will be the maximum length, right? The second layer, it will be LSTM, 128 units. I used the dropout, and I used also something called the recurrent dropout. Maybe it's dropout and recurrent dropout. Maybe you need to dive into it to understand the difference. Maybe this is for the input. Maybe this recurrent dropout is for the this one. It's for the recurrent weights, correct? So this one for the input weights, this one for the recurrent weights, and the factor here equal 0.2, which means we will drop out 20% of those weights in the training process. The output will be a dense layer. It's a sigmoid, whatever, or so it should be, in fact, because we need to do this sentiment analysis, so the output should be maybe +1 and 0, correct? And the output, it will be just one output. We will train the model, binary cross entropy. We trained the model. This is the embedding, number of parameters in the embedding layer, right? It's maximum length equal 100, right? So this maximum length, it's a embedding layer. In fact, it's feed-forward neural network. So the input will be 128, the output will be 100, right? So in this case, number of parameters here, it will be okay. No, sorry. I mean, the output is 128. The output is 120. Maximum number of words, it's 120. No, sorry. It's the length of each word will be 128, and number of words it's 20,000 because the dictionary is 20,000, right? So number of parameters here will be this number. It will be 20,000 multiplied by 128. For the LSTM, it has 128 units, and the number of inputs it's 128. In fact, so if you need to get this number, maybe it's explained in the next page. Okay. but no problem. It's 128. First, it's 128 multiplied by 128 plus 128 multiplied by 128 plus 128. You will get this number. For the output layer, it's 1 multiplied by 128 plus 1, so it will be 129. So we will train the model and we will evaluate the model with my test set. We get this test score and accuracy and stuff like this. So this is the confusion matrix, right? We have sentiment analysis. It's positive and negative. So you can see that across this diagonal, we have 25,000 data points or samples in the test set. So you can see that, I mean, it's very good accuracy, in fact. So the accuracy, it's around 75%, right? Precision and recall, it's 70%, 88%. But just remember that we trained this model for, how many? Yes, 10 epoch. We trained this model for 10 epoch. I mean, the batch size, it's mini batch gradient. So, I mean, the batch size equals 32 because maybe if you will increase this batch size too much, maybe it will be too heavy for maybe the memory. We have the F score, so the F score will be 78%. And as I told you before, the F score, it's just one way for combining precision and recall into a single number. The embedding layer, so just to explain the embedding layer, so the input dimension, it's the maximum words. So this is the input features, it's maximum words, which is 20,000. This is the dimension of my dictionary. We decided this input dimension will be 20,000 because I decided to use my dictionary size will be 20,000 most common, most popular words. 128, it's the output dimension, the embedding size. So each word will be represented in a vector of size 128, right? You can decrease this one if you want. So the input length, it's the maximum length, which is 100 words. If you want to define a temp model, and if you want to see the output from this word embedding, so I have a temp model, the input, it's model input. The output, it's the output from layer 0, which is the embedding layer. If I want to predict, I want to see how it looks like. So X test, this is my first sentence, my first review, for example, X test 0, for example, I will send it and I will see the word embedding size. So, each review consists of 100 words, where each word will be encoded into a vector of length of 128. So the size of this one will be 100 times 128, correct? It will be 100 times 128. So because I decided that the maximum length of each review, it's 100. So when we do this word embedding, so the output will be 100 times 128, which means each word will be represented by a vector of size 128. I mean, this is, I try to plot this, loss and accuracy for the training and the validation, correct? And it's clear that maybe we'll have some overfitting here. I need to train the model more. Maybe I need to, oh, we finished. Okay, that's very quick. Yes. So please, if you have any, we finished early, in fact. So if you can, please, if you have any questions, we can discuss it. If not, we can get another slide. Any questions, please? Any questions?
A question from my side.
Yes, please. No questions? Okay, so now we finished the RNN. RNN was very, very important. And if you want to use LSTM, it's the same. I mean, no difference if you want to use simple RNN or GRU or well, I saw that we have some examples for LSTM, but it's the same. I mean, no difference at all. We just need to replace simple RNN with GRU and LSTM. But in this example, yes, I used the LSTM. In fact, yes, I'm so sorry, because in this example I used LSTM, right? So in this example here, I used LSTM, right? So calculating those numbers, for calculating those number of weights, it's more complex. It's not that easy. So we need to go to the model and we need to see how can we, I thought that it's, I thought that it's simple RNN. It's LSTM model. We used here LSTM, right? So this layer, it's LSTM. So to get this number, we just need to go to the equations of LSTM and see how can we get this number. And as you can see here, when we are using LSTM, number of parameters will be too much. It's much higher. And this LSTM is more efficient for, representing, it has better capability for memorizing those context. And also it's much better in terms of vanishing gradient and exploding gradient. So the performance should be much better. So RNN is very important and very, very important. But if you don't have any questions, maybe I can go to another stuff, this patch normalization, right? Because if we don't have time for, because next week I will take it off because I have some meetings. So maybe we will meet another, maybe 1 week or 2 weeks again. But if you don't have any questions, maybe I can talk about batch normalization because we didn't talk about it, right? So I can use this batch normalization. We didn't talk about it. It's something which is also very important for the performance models. Can you see my screen?
Yes.
Yes.
Okay. I need to put it